Hello everyone and welcome to another tutorial. Today we're going to have a look at the knitting pattern animation, and to accomplish this effect we'll have to replicate one curve pattern in Bifrost and then make a duplicate of it and lerp these two positions so we're getting this animation. And then we can go ahead and tweak the graph to give us strands around strands and randomize them, make that animation a little bit more interesting by displacing the strands while they are animating. And we can also go ahead and cut out a shape or maybe animate the target mesh or the target strands, like a wave pattern or something, to make that a little bit more interesting. So yeah, let's go ahead and have a look at the original graph and at the different stages that we have to implement to get this working. All right. Okay, so I started with a simple curve in Maya, which is my knitting pattern. And what I want to do is replicate this on the x-axis and then combine all these points to one long strand, and then take the strand and replicate it on the z-axis. So we're getting an interlocking pattern. So in the graph, I imported the curve here and made that knitting pattern. And this is what it's going to look like once it's replicated on the x-axis. And then I replicated this whole thing on the z-axis. And this is essentially our target mesh. We're going to duplicate these strands or make a copy that is a straight strand with the same amount of points and place it somewhere else in the in world space, and then lerp the point positions towards our goal. Here we can see the straight copy of my strands. I already attached a locator in Maya, so I can change its starting position and maybe, make that a little bit more interesting once everything is set up. And somewhere down the line, we can see that they're animating towards the goal. And the way I did it was to use a planar field. And I use the primitive fall-off shape in Maya 2022 to get a nice gizmo in the viewport. And I kind of rebuilt this field in Bifrost. Here you can see the weights of the scalar field, which is 0 at the starting plane and 1 at the other plane here. And you can scale the field to spread out those scalar values. So this is animated. It's animating through our straight strands and animating the fraction or the weight for the lerp to animate these points towards the goal. And this is the basic setup, and from there on we can go ahead and go crazy with it. Here I already implemented some offset for the weight, so all the strands have a different timing. And what we can also do is displace these strands while they're animating. So it should be a displace node somewhere in here. I turned off for now, but if I activate it, you can see that they're straight in the beginning, and going to be displaced while they're animating, and they're neatly going to fit into their target pattern in the end. And then we can also animate our target. So there's another displacement node where I fed in a sine field. And this is a locator to change the position or the scale of the sine. And somewhere in the beginning of the graph, we could also take a poly shape and delete all the points that we don't want. So we could use cutting geometry to make another shape for our target. And then later, down the stream, I made strands around strands. And then displaced it as well. And then we're getting what you saw on the render. So let's start with a clean graph and make ourselves that netting pattern. Take our input curve and then what we want to do is get the point positions. And getting the first and the last point and calculate their distance on the x-axis. So we can get the first point in the array and the last point in the array and split up that vector 3 into scalar values. If you subtract the x position from each other, you should get the distance, since we need an absolute value. Just hook that up. And then we can create ourselves a point geometry where we can scatter this pattern and then later recombine it to a strand. So I'm going to fill an interpolated array, start with 0, and I'm going to end with the number of points or replications that we want to create and multiply that by the offset that we just calculated here. So we can take an input node, so we can change the size. Number of replicants on the x-axis. Convert that to float, so we can multiply it. Into the second input of the interpolated array. By the way, since this is just the x-axis, we might need to create a vector again, so we're getting proper points. So scale out to vector 3. We can keep y and z 0, and we can take the calculated x position, and then we can construct a point object. Construct points. And then let's give ourselves 10 points. Then we can already go ahead and take our input curve and use that as a instance shape. And then we can go ahead and use our original curve as instance geometry for our points. So set instance geometry, feed in the points, get the original curve, as instance geometry. Let's have a look at that. Okay, that does seem to be a little bit off. I think the total value that we're multiplying to get the distance for all 10 points needs to be one less, because the first one's not going to be moved. So yeah, we have to decrement the number that we put in by 1, and then it should match up. Yeah, okay, great. So we have our instances, and we're getting their point position. And then we can construct a strand. We might need to bake them before we do. So we bake an instance geometry, 2 strands, getting the point positions, and then creating a 1 long strand. Awesome. Okay, so that's the first axis. We can package all of that into a compound. We'll call it knit. And then we make a for each loop, put in the strands, and replicate it. The number of iterations is going to be the replicants on the z-axis. So we're getting the point position of the strand for each loop and adding an offset on the z-axis. So that's the point position. And we're going to add another vector, which is a value that we specify times the current index on the z-axis, and we leave the rest alone. So like that, an offset z, and multiply it with the current index. It needs to be a float. And we're setting point position. And then we're getting, let's say, another 10 replicants on the z-axis. So this should be an array of 10 strands now. Oops. And the offset, something that we can play around with. So yeah, that's our target pattern for our animation. Save it. Next up is going to be the straight copies of our strands that we animate. So for each strand that we have, make that iteration target. We're getting the point position. And we could get the first point and the last point of each strand, and then connect them make a new strand and resample those. So we're getting the same number of points as the original strand. So let's get the first point and the last. And fill interpolated array. First one is here, second one is there. And the number of points that we want to generate is the point count, basically. So the point count of the strand. And construct a new strand from there. So yeah, these are the straight copies. And then we simply have to transform them. Transform points. Now we have to make them. I have to merge them. Since this is an array, I want to have one long strand. Just merge them together. We need to do this on the upper stream as well. That's the wrong type. Okay. So for the transform, we make ourselves an input and create a locator. And hook that up to our Bifrost graph. Load matrix into the transform input. And then we can move our copies. Just like that. Okay, so now that we have our animation geometry and our target, we'll just have to lerp the positions from here to there. So we'll have to compute this for each strand, so we can put in some offsets and other things. I made myself for each strand compound, make that editable. I'm going to show you what it does. It's taking a strand, getting its structure, and then looping through all these strands. So this is the strand count. We're looping through all the strands and accessing that offset array, so only that portion of the strand, and slicing up all the properties that we want to compute. So in this instance, what we want to get is the point position. So we're getting the point position of each individual strand. Get the slice. So what we have here is the point position array of the current strand that we computing in this loop. And what we also need is our target. So that's the strand that we are computing. And take these strands in as target. We're getting the target's points position. Slice them too. And in here, we create the lerp node. And then we're lerping from our strands to our target strands. The fraction is the parameter that we want to drive with our field. And we can already go ahead and make that a float, a single float value. And what we need is a field in here, and sample that field with the point positions. So we're sampling the field by our point position, and the result is going to be the fraction. We're going to pipe out the field. And hook that up later. Since all our strands are going to be computed in a for loop, what we're getting is the point positions as a 2D array. So we have to flatten the point positions again and set the point position back onto our strands. And now let's build ourselves the planar field. So I do have the primitive offset node already in place. And then we need to replicate the shape, its orientation, and make that a planar field in Bifrost. So we take the planar fields, and the fall off. Oh, let's create a new one. If you create a new primitive fall off in Maya, what you're getting is a sphere, and you can change that primitive to be a plane, and its default orientation is going to be pointing towards the x-axis, and it's going to be 2 units wide and 2 units high. So for our planar field, we want to point it into the same direction, make that normal pointing to the x-axis. And then get a field scope to see what we're doing. Make a scalar field scope. Terminal. Right. So now it's using the bounds that are in the scalar field scope node. But what I would like to have is a nice gizmo that gives us only a few samples between these two planes, and we'd have to rebuild this as well. So make a polyplane or a mesh plane in Bifrost. And since this fall-off shape has a dimension of 2, we make that here as well. And the up axis is going to be x again. Let me show that. And this is what we're getting. And then we can use that as a bounce geometry, probe geometry, sorry, for our diagnostic. Now we're not seeing anything because right at this point, the values in our scalar field are 0, so we're not getting any points. But what we can do is replicate that plane a couple of times, so we're getting more points that we can use as a probe geometry. So we do the same thing as we did with the strands. We're going to take the mesh and replicate it a couple of times on the x-axis. get the point positions. And add a vector. And multiply it with the count of the current index. Set point position. Simply merge geometry should suffice. So now we're getting something. Okay. And then we simply need to transform the planar fields and the mesh plane as well. So transform field, it's going to go here. Transform points, it's going to go there. Then we can hook up the transform with an input node and connect our primitive fall-off transform. Move matrix to transform 1. And that's it. And that's our fields. So let's pack this up. As a compound. Planar fields, or planar fall-off. And for an output, we need the field, of course. And feed that back into our strand animation. And now we can move it and see that it's already doing something, but we're getting values in the negative space, and of course we're getting even more weight on the positive x-axis. So we need to restrict it. Let's hop into our animation compound, where we have our lerp node and the field samples. And then we can set range. Change range. Feed in the values and make those from 0 to 1. Keep the clamp. And this should do the trick. Yes. So now they're animating from their start position to their goal. And I always like to have an F-curve in here, so we can change the way it's animating. Start a little bit slower. Yeah, something like this. And then we can already go ahead and make some variation. Since we are already in the loop for each strand, we can simply create a random value and take the current index as an input for the index. So this will change for each strand, and add some random value onto our sample field. This could be something from 0.2 to 0.2 maybe. Let's add it to the field, feed it into the range node, and then we're having some offsets. That's great. But what I don't like is the way these wavy patterns are lerping towards their goal position. It's a bit too early for my taste. They could be more straight. And to give us some control over this, we can use one of Maxime's nodes, which is called smooth strands, and simply smooth them out. But we'll have to also connect our weight and maybe make another F-curve to control this properly, because it should actually be smoothed while it's animating, and then stop the smooth once they're reaching their goal position. So let's get our weight, the unmanipulated weight without the F-curve, out for our animation compound. Yeah, we have to flatten these as well, because it's a 2D array. Out weight, and we can feed that back into the smooth strand node. And we might have to reverse it, yeah. So it's 1 minus the weight. Okay, so this can straighten our curves while they're animating. Nice, cool. Yeah, that's it. Now we have everything in place to make this effect work. And now comes the fun part. We can play with all these parameters and change it up and add some secondary strands around these. And oh yeah, they're still pretty blocky. So let's get another one of Maxime's strands. Create cut-more-wrong strands. So we might need to make another for each strand node. And for this one, we're not going to set the position or anything. We're simply going to get the point position of each strand. And on this level, we're going to take this as input points or control points for the cut-more-wrong strands. We can do that in here, actually. And then we're not outputting the array, but we're outputting the cut-more-wrong strand. And then what we're getting is a smooth copy of the strands we had earlier. Right. So how about we deform our target? That's this stream here. We can displace it by another custom field that we're building. So let's get another plane field and field scope for the scalar values. Okay. Then we can make a gradient out of these scalar fields. Make a gradient field, feed in the scalar. Make a vector field scope. And this will give us our vectors along the normal that we put into the plane field, so they're pointing up. That's good. We want to push all of our strands up, but with a sine curve. So how do we make a sine wave out of this? We simply can take all these vectors that are pointing up and then multiplying them with a scalar field that has a sine wave in it. So let's make another planar field, and this time we're not going to point up in y, but we are going to point into the x-axis, because this is the axis on where we want to create our sine wave. And simply take a sine, put in the planar field, have a look at the scalar values it is producing. And then we can already see that this is a sine wave. The values are 1 where it's red, and the values are decreasing towards 0 where we don't see any samples. And yeah, we simply multiply that scalar value with the vector fields. And this just gives us vectors that are altering between the full vector pointing towards 1 and then decreasing again. And then we can make a transform for the sine, so we can manipulate it in the viewport with another locator maybe. So transform field, look this up, make another input node for an additional transform, create a locator. Let's sine, look, and take that world matrix into the new transform input. So now we can scale it up and also turn it maybe. Yeah, we'll see. Let's get this vector into the point displace. Get rid of the field scope. I think we can clearly see what it is doing now. So yeah, we can change the waviness, change the direction, and animate it, of course. So let's just set keyframes from here to there, maybe scale it. And let's get the other transform. Have a follow field and animate this too. Okay. So that's what we're getting. Okay, so that's our sine field. Let's save it. Okay, so let's make some strands around strands. There's a Rebel pack node to do this. Create strands around strands. And since the output here is an array, we might need to merge it. And if we hook this up, I think nothing's gonna show up, because this compound is going to need some more information. If we're having a look at the strands right now, it's pretty basic structure, and we might need an orientation and a point ratio and maybe a point size to get this working. So we can update strand bases and the ratio, update point strand ratio. Now this is a node that was previously accessible, but the current version of Bifrost, this is just an internal compound, but you can get it off of another node. So I think it's the set strand size profile. Dive into this compound and either get the checkpoint ratio, or you can dive deeper and get the update strand ratio from here and use this one. Are we already getting some plies? Let's see if we can manipulate the radius. Oh yeah, we can. Cool, so maybe make 10 plies and give it some more twist, like that. And then, to make this a little bit more interesting, we could also displace the plies. And to do this, we want to push them away from the original curve, the one that's still visible in the middle here. So we can simply take the point position of the ply strands and then sample the closest location on the original strand and form a vector between the 2 points to push the others out. And yeah, let's make a compound straight away. Displace ply. So let's apply strands, and this is the original strand. Again, point position of the plies. And getting closest locations from the original strand. Sample property. Make that a flow 3, because we're getting the point positions. And then we can subtract the point from the ply from the closest point on the original strand, and this will give us a vector. And then we can displace applies by that vector. And this should push them out. Yeah, great. So now we simply have to change the weight on this displace node, and we can do that by sampling a turbulence field, for instance. Since this is a vector, we want to get its length. So that's the scalar field now. And then sample the fields at the same point positions. And use that as weight. So now if we increase the magnitude on the field and play around with the number of frequencies and the ratio, we should get some interesting effects. Maybe we can also make another F-curve. And let's keep the magnitude to 1. So the curve will also be from 0 to 1. Maybe I'll make something like this and increase the scale on the displace node. Yeah. Quite interesting. Okay, so what's next? Maybe we can have a look at the animation of our strands. We straighten them up before, but we can also use the weight that we're computing from our planar field to introduce some displacement along the way. So let's disconnect the plies for now and concentrate on the original strands again. That's somewhere in here. So this is where we smooth them. And yeah, we can displace points in between, get the weights, and feed them to an F-curve. And so at the beginning of the animation, we don't want them to be displaced. And at the end of the animation, when they are reaching their goal, they should not be displaced as well. But in between, we can introduce some displacement. Like this. And for a vector, we can also take another turbulence field maybe. Maybe we should do it after this move. That makes sense. Okay, so maybe this way around. Yeah. Increase the magnitude. Less frequencies maybe. Very nice. Okay. And if you want, you can also play with the start position. We're already having a locator for this, so you can spread them out and maybe change the slope. And now let's give ourselves some more surface area to work with. So increase the number of replicants on both axes, like this. And let's cut out a shape, maybe. So make a cube. Like this. And then maybe make that see-through and put that into our graph. And early in the beginning, when we are building our strands, we can actually kill some of the points. So in here, where we're replicating the one long strand on the x-axis 10 times or 20 times for the z-axis, we are already having point positions. And since we cannot simply delete the points on the strand, we can construct an intermediate point object and use a rebel pack node, collect points in the mesh. So we feed in our intermediate points and the mesh. And then you can also make this editable, because the point collection is going to be some property on our shape, but we're interested in the indices. So we can pipe them out and get the delete points node. We can just simply feed in the indices. That's the right output. And then get the resulting point properties and construct the strand. And I'll simply invert the collection. And this is the way to cut them. Okay. Maybe undo the crazy transformation I did previously. Yeah, so now we have everything in place. We have an animated target object that is cut out by our custom shape. We have some displacement and some offsets in the animation. And we're having strands around strands that are also being displaced somewhat. And then it's a simple matter of extruding the strands. And then you can maybe reverse normals. Yeah, go ahead and maybe resample if you don't like the tessellation on this, and cache it out and do some nice renderings with your favorite rendering software. Okay guys, that's it. Have fun.